All right, ladies and gentlemen, we're going to be looking at ionization energy down a group. So, as before, remember this is a group going down, this is a period going across. So the first thing to do, of course, is to define ionization energy. So ionization energy is the energy required to remove one electron from a neutral atom. There's a slightly more technical definition, excuse me, but that will work. Now, let's use beryllium for this one. So let's say you have a neutral atom of beryllium. Well, we find beryllium on the periodic chart. There it is. Beryllium has 4 protons and 4 electrons. So that means that beryllium has a charge of positive 4 in the nucleus because of the 4 protons. Then it's got 1, 2, 3, 4 electrons. Now, imagine that you use a force, usually, excuse me, it's electricity, but you use a force to basically push that electron out. So that electron leaves. Well, what happens then is now beryllium has lost an electron. It still has the same positive 4 in the nucleus, but now it only has 3 electrons there. And 1 electron has been lost. So now beryllium is not neutral. Beryllium is instead a positive charge or a cation. So beryllium has a positive charge, and that 1 electron has been lost. The energy required to do that, or if you want to think of it this way, the pull that's required to pull that electron away, that is ionization energy. So let's use for our examples beryllium and magnesium. And in the periodic table, here's beryllium with 4 electrons, here's magnesium with 12. Now the same rules apply as before. Positive 4, 1, 2, 3, 4. I go down to magnesium, positive 12 in the nucleus, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so what is happening with this trend for ionization energy as you go down? Well, basically what's going on is this. For beryllium, you have a very small atom. And so the attraction between the electrons on the outside and the positive 4 in the nucleus is actually pretty big, okay? Large attractive force. Because the atomic radius is small. They're very close together, so therefore they're attracted to each other. The opposite, of course, is occurring for magnesium. Here, the atomic radius for magnesium is bigger, so the nucleus is further away. From that electron, and so you have a smaller attractive force. Because that attractive force is smaller, it means that as you go down the group, the ionization energy decreases. So, down the group, the ionization energy decreases. Now, why is that? This is a small atomic radius because it only has 2 energy levels. This is a larger atomic radius because it has 3 energy levels. And so the valence, or outside electron, is further from the positive nucleus and takes less energy to remove. Easier to remove electrons as you go down the group. And that's it for that one.